If we're interested in studying reaction kinetics in a system where there's significant internal resistance to transport, the results can be very misleading. We saw previously that in the limit of high Thiele modulus, the effectiveness factor is given as the reciprocal of the Thiele modulus. Since the definition of the effectiveness factor is the observed or actual reaction rate divided by the rate with no gradients, we can write the observed reaction rate as 1 over the Thiele modulus times the rate without gradients. We previously saw that the generalized Thiele modulus can be written in the following form. Where L is the characteristic length scale for diffusion, N is the order of the reaction, and DAE is the effective diffusivity of A through the system. So if we had no external transport restrictions, that would be that CAS here would be equal to the bulk concentration of A. The observed rate can be written as 1 over the Thiele modulus times the reaction rate constant K times the concentration of A in the bulk to some reaction order. Plugging in our expression for the generalized Thiele modulus, we can write we can combine some terms to simplify our expression. And so looking at this rate expression, we can see that the rate is proportional to the concentration of A to the n plus 1 over 2 power. And this is for a reaction that has a true reaction order of n. So this means that internal transport limitations can disguise the true reaction order that we measure. Similarly, we can see that the temperature dependence of the rate is modified compared to a system without internal transport constraints. Since K has an exponential dependence on temperature, it will dominate the observed temperature dependence. So here, since the observed rate is proportional to the reaction rate constant to the 1/2, and the reaction rate constant follows an Arrhenius type relationship, we'll measure an activation energy that's 1/2 of the true activation energy. So this plot shows what this might look like experimentally. At low temperature, kinetic reaction rates are comparatively slow, so the system is at a low Thiele modulus. Here, the true activation energy is measured. At high temperatures, kinetic rates increase to the point of incurring transport limitations, and the observed activation energy becomes modified by the Thiele modulus, giving 1/2 the true kinetic barrier. The observed rate expression also gives us a way to check for transport restrictions. Under these conditions, the rate depends on the characteristic diffusion length. By lowering particle size, this can be changed. If changing particle size modifies the rate, this is a good indication that transport limitations are significant. So here we've seen how internal transport limitations can corrupt kinetic analysis, and also a simple way that we can check for the presence of these transport limitations.